Hello and welcome. In this video, we'll be diving into the fascinating world of complex numbers and polynomials. These concepts are fundamental in higher-level mathematics and have wide-ranging applications in science and engineering. By the end of this session, you will be able to solve quadratic equations with no real solutions, perform basic operations with complex numbers, understand the properties of complex conjugates, and master polynomial addition, subtraction, multiplication, and division. Let's begin with our first topic, solving quadratic equations that don't have real solutions. Our first objective is to solve quadratic equations where the discriminant is negative. You'll recall from your previous studies that for a quadratic equation in the form ax squared plus bx plus c equals 0, the solutions are given by the quadratic formula. The formula is x equals negative b plus or minus the square root of the discriminant, all divided by 2a. The discriminant, which we denote with the Greek letter delta, is b squared minus 4ac. The value of the discriminant tells us about the nature of the solutions. If the discriminant is positive, we get two distinct real solutions. If it's 0, we get two identical real solutions. But what happens if the discriminant is negative? In the realm of real numbers, we say there are no real solutions, because you cannot take the square root of a negative number. This is where imaginary numbers come in. In 1572, Raphael Bombelli introduced the imaginary number, I. He defined I as the square root of -1. This single definition opens up a whole new world of numbers. It's called imaginary, because it doesn't fit on the standard real number line. With I defined, we can now find solutions for quadratic equations with a negative discriminant. These solutions are called complex numbers. A complex number is any number that can be written in the form a plus b, where a and b are real numbers. A is called the real part, and b is called the imaginary part. This means every real number is a complex number, where the imaginary part, b, is 0. Let's see this in action with an example. Consider the equation x squared equals -4. To solve for x, we take the square root of both sides, giving us x equals plus or minus the square root of -4. We can rewrite the square root of -4 as the square root of 4 times the square root of -1. We know the square root of 4 is 2, and we've just defined the square root of -1 as I. So the solutions are x equals plus or minus 2i. These are two purely imaginary solutions. Let's try a more complex example using the quadratic formula. Solve the equation z squared plus z plus 2 equals 0. Here, a is 1, b is 1, and c is 2. Let's calculate the discriminant. The discriminant is b squared minus 4ac, which is 1 squared minus 4 times 1 times 2. This simplifies to 1 minus 8, which is -7. As expected, the discriminant is negative. Now, we substitute these values into the quadratic formula. We get z equals -1 plus or minus the square root of -7, all divided by 2. We can rewrite the square root of -7 as the square root of 7 times I. So our solutions are z equals -1 plus or minus I times the square root of 7, all over 2. To write this in the standard a plus b form, we separate the real and imaginary parts. The solutions are z equals -1/2 plus I times the square root of 7 over 2, and z equals -1/2 minus I times the square root of 7 over 2. These are two complex solutions, so we have successfully solved quadratic equations with negative discriminants by introducing the imaginary number I. We have met our first objective. Now that we can find complex roots, let's see how to use them to factor polynomials. This is our second objective. We're going to learn how to write polynomials as a product of linear factors, even when the roots are complex. You're familiar with the difference of two squares factorization. The difference of two squares, a squared minus b squared, factors into a plus b times a minus b. This is a powerful tool for factoring. But what about the sum of two squares? For example, x squared plus 4. In the real number system, this is irreducible. It doesn't factor. However, in the complex number system, we can factor it. We use the fact that I squared equals -1. This means negative I squared is positive 1. So we can rewrite plus 4 as minus 4i squared. Now we have x squared minus 4i squared, which is a difference of 2 squares. This factors into x plus 2i times x minus 2i. So the sum of 2 squares can be factored in the complex number system. Let's apply this to solve some equations. Solve x squared plus 9 equals 0. We can rewrite this as x squared minus 9 I squared equals 0. This factors into x plus 3 I times x minus 3 I equals 0. Setting each factor to 0 gives us the solutions x equals plus or minus 3i. This technique is also useful for higher degree polynomials. Consider x cubed plus 2x equals 0. First, we can factor out an x, leaving x times the quantity x squared plus 2 equals 0. One solution is clearly x equals 0. For the other solutions, we solve x squared plus 2 equals 0. We rewrite this as x squared minus 2 I squared equals 0. This factors into x plus I times the square root of 2 times x minus I times the square root of 2 equals 0. This gives us the solutions x equals plus or minus I times the square root of 2. So the cubic equation x cubed plus 2x equals 0 has 3 solutions. One real solution, x equals 0, and 2 complex solutions, x equals plus or minus I times the square root of 2. We have now seen how to factor polynomials using complex numbers, achieving our second objective. Now, let's formalize our understanding of complex numbers and their operations. This is our third objective. We'll define the real and imaginary parts of a complex number and learn how to add, subtract, multiply, and divide them. As we discussed, a complex number z is written as a plus bi, where a is the real part and b is the imaginary part. We write this as re of z equals a and I, m of z equals b. For example, if z equals 2 plus 3i, its real part is 2 and its imaginary part is 3. If z equals negative I times the square root of 2, its real part is 0 and its imaginary part is negative square root of 2. This is a purely imaginary number. Operations with complex numbers are very similar to operations with radicals, with the key difference being that I squared equals negative 1. To add or subtract complex numbers, you simply add or subtract their corresponding real and imaginary parts. It's like collecting like terms. For multiplication, you use the distributive property just like you would with two binomials. Remember to substitute I squared with negative 1. Division is a bit more involved. To divide by a complex number, we use a special technique called multiplying by the complex conjugate. The complex conjugate of a plus bi is a minus bi. We multiply both the numerator and the denominator by the conjugate of the denominator. This makes the denominator a real number, simplifying the expression. Let's work through an example that uses all these operations. Let z equal 3 plus 2i and w equal 4 minus I. We'll find their sum, difference, product, and quotient. First, the sum. We add the real parts, 3 and 4, to get 7. We add the imaginary parts, 2 and negative 1, to get 1. So z plus w is 7 plus I. Next, the difference. We subtract the real parts, 3 minus 4, to get negative 1. We subtract the imaginary parts, 2 minus negative 1, which is 2 plus 1, to get 3. So z minus w is negative 1 plus 3i. Now for the product. We use the distributive property. 3 times 4 is 12. 3 times negative I is negative 3i. 2i times 4 is 8i. And 2i times negative I is negative 2i squared. Since I squared is negative 1, negative 2i squared is positive 2. Combining the real parts, 12 plus 2 is 14. Combining the imaginary parts, negative 3i plus 8i is 5i. The product is 14 plus 5i. Finally, the quotient. We multiply the numerator and denominator by the conjugate of the denominator, which is 4 plus I. In the numerator, we get 12 plus 3i plus 8i plus 2i squared, which simplifies to 10 plus 11i. In the denominator, we have a difference of two squares, 4 squared minus I squared, which is 16 minus negative 1, or 17. So the quotient is 10 plus 11i over 17, or 10 seventeenths plus 11 seventeenths 1. We have now successfully performed all four basic operations with complex numbers, achieving our third objective. Let's move on to our fourth objective, understanding the equality of complex numbers and using it to solve for unknown variables. The rule for equality is very simple. Two complex numbers are equal, if and only if their real parts are equal and their imaginary parts are equal. This is a powerful tool for solving equations. In other words, if a plus bi equals c plus di, then it must be true that a equals c and b equals d. This allows us to turn one complex equation into two real equations. Let's see how this works with an example. Find real numbers x and y such that the product of x plus yi and 2 minus I equals negative I. Our goal is to find the values of x and y. First, let's expand the left side of the equation. We get 2x minus xi plus 2yi minus yi squared. Since I squared is negative 1, minus yi squared becomes plus y. Rearranging the terms, we group the real parts and the imaginary parts. The left side is 2x plus y plus 2y minus xi. Now, we set this equal to the right side, which is negative I. We can write negative I as 0 minus 1i to make the real part explicit. Using the equality rule, we equate the real parts and the imaginary parts. This gives us a system of two linear equations, 2x plus y equals 0, and 2y minus x equals negative 1. We can solve this system. From the first equation, y equals negative 2x. Substituting this into the second equation gives 2 times negative 2x minus x equals negative 1. This simplifies to negative 4x minus x equals negative 1, or negative 5x equals negative 1. So x equals 1-5. Now we find y. Since y equals negative 2x, y equals negative 2 times 1/5, which is negative 2/5. So the real numbers are x equals 1/5 and y equals negative 2/5. This example shows how the equality of complex numbers allows us to solve for real variables within a complex equation. We have now met our fourth objective. Let's now explore a very important concept, complex conjugates. This is our fifth objective. We'll define complex conjugates and see how they are used, especially in relation to quadratic equations. As we saw with division, the complex conjugate of a number z equals a plus bi is z star, which equals a minus bi. You simply change the sign of the imaginary part. Complex conjugates have a crucial property related to quadratic equations with real coefficients. The theorem states that if a quadratic equation has real coefficients, and one of its roots is a complex number c plus di, then its conjugate, c minus di, must also be a root. Complex roots always come in conjugate pairs. Let's prove this. Suppose z equals c plus di is a root of the equation ax squared plus bx plus c equals 0, where a, b, and c are real. This means that when we substitute z into the equation, it holds true. So, a times z squared plus b times z plus c equals 0. Now, let's take the conjugate of both sides of this equation. The conjugate of 0 is just 0. On the left side, we can use the properties of conjugates we'll explore later, which state that the conjugate of a sum is the sum of the conjugates, and the conjugate of a product is the product of the conjugates. This allows us to distribute the conjugate. We get a star times z star squared plus b star times z star plus c star equals 0. Since a, b, and c are real numbers, their conjugates are just themselves. So a star is a, b star is b, and c star is c. This final equation shows that z star, the conjugate of z, also satisfies the original quadratic equation. Therefore, z star is also a root. This proves the theorem. This theorem is incredibly useful. If you know one complex root of a real quadratic, you automatically know the other. For example, if 1 minus 2i is a root of a real quadratic equation, then its conjugate, 1 plus 2i, must also be a root. This allows us to reconstruct the equation. The sum of the roots is 1 minus 2i plus 1 plus 2i, which is 2. The product of the roots is 1 minus 2i times 1 plus 2i, which is a difference of two squares, 1 squared minus 2i squared, which is 1 minus negative 4, or 5. A quadratic equation can be written as x squared minus the sum of the roots times x plus the product of the roots equals 0. Substituting our values, we get x squared minus 2x plus 5 equals 0. Any real multiple of this equation is also a valid answer. We have now defined complex conjugates and proven the conjugate root theorem, meeting our fifth objective. Let's now investigate the properties of complex conjugates. This is our sixth objective. We'll look at how conjugation interacts with addition, subtraction, multiplication, and division. Let's define two complex numbers, z1 and z2. Let z1 be a plus bi and z2 be c plus di. Their conjugates are z1 star equals a minus bi and z2 star equals c minus di. First, let's consider the conjugate of a sum. The conjugate of z1 plus z2 is the conjugate of a plus c plus b plus di. This is a plus c minus b plus di. We can rearrange this as a minus bi plus c minus di, which is z1 star plus z2 star. So, the conjugate of a sum is the sum of the conjugates. Next, let's look at the conjugate of a product. The conjugate of z1 times z2 is the conjugate of ac minus bd plus ad plus bci. This is ac minus bd minus ad plus bci. Now let's calculate the product of the conjugates z1 star times z2 star. This is a minus bi times c minus di, which expands to ac minus bd minus ad plus bci. The results are identical, so the conjugate of a product is the product of the conjugates. These two properties, along with the fact that the conjugate of a conjugate is the original number, allow us to derive other properties. For example, the conjugate of a difference is the difference of the conjugates, and the conjugate of a quotient is the quotient of the conjugates. Also, the conjugate of a power is the power of the conjugate. These rules are very useful for simplifying complex expressions. Let's use these properties to simplify a complex expression. Simplify the expression w star minus z conjugate minus w minus 2z star. First, we distribute the conjugate on the first term. The conjugate of a difference is the difference of the conjugates. So we get the conjugate of w star minus the conjugate of z. The conjugate of w star is just w. So the first term simplifies to w minus z star. Now we distribute the negative sign. We get w minus z star minus w plus 2z star. The w and negative w cancel out, and negative z star plus 2z star is z star. The entire expression simplifies to z star. We have now investigated the properties of complex conjugates and seen how to use them to simplify expressions, meeting our sixth objective. Let's now shift our focus to polynomials. This is our seventh objective. We'll define what a polynomial is and learn how to add, subtract, and multiply them. A polynomial function is a function of this form. It's a sum of terms, where each term is a constant coefficient times a non-negative integer power of the variable x. Here, x is the variable. v, a, values are the coefficients, which are real numbers. The highest power of x, n, is the degree of the polynomial. The coefficient of the highest power, a underscore n, is called the leading coefficient. You're already familiar with some low-degree polynomials. A degree 1 polynomial is linear, a degree 2 polynomial is quadratic, a degree 3 polynomial is cubic, and a degree 4 polynomial is quartic. Adding and subtracting polynomials is straightforward. You just collect like terms. Let's find the sum and difference of these two polynomials, p of x and q of x. For the sum, we add the coefficients of the x cubed terms, the x squared terms, and so on. 1 plus 2 is 3. Negative 2 plus 1 is negative 1. 3 plus 0 is 3. And negative 5 plus negative 11 is negative 16. The sum is 3x cubed minus x squared plus 3x minus 16. For the difference, it's crucial to distribute the negative sign to every term in q of x. So we have x cubed minus 2x cubed, which is negative x cubed. Negative 2x squared minus x squared is negative 3x squared. 3x minus 0 is 3x. And negative 5 minus negative 11 is negative 5 plus 11, which is 6. The difference is negative x cubed minus 3x squared plus 3x plus 6. Now let's look at polynomial multiplication. To multiply two polynomials, you multiply each term of the first polynomial by each term of the second polynomial, and then collect like terms. This is often called the distributive property, or FOIL for binomials. Let's find the product of p of x and q of x. We'll multiply each term in p of x by each term in q of x. First, we multiply x cubed by each term in q of x. Then, we multiply negative 2x by each term in q of x. Finally, we multiply 4 by each term in q of x. This gives us 3 rows of terms. Now we collect the like terms. The x to the 5th term is 2x to the 5th. The x to the 4th term is 3x to the 4th. The x cubed terms are negative 5x cubed and negative 4x cubed, which sum to negative 9x cubed. The x squared terms are negative 6x squared and 8x squared, which sum to 2x squared. The x terms are 10x and 12x, which sum to 22x. And the constant term is negative 20. The final product is 2x to the 5th plus 3x to the 4th minus 9x cubed plus 2x squared plus 22x minus 20. We have now defined polynomials and performed addition, subtraction, and multiplication, meeting our 7th objective. Our final objective is to master polynomial division. This is a more complex operation, but it's essential for finding roots and factoring polynomials. We'll learn the long division algorithm for polynomials, which is very similar to the long division you learned for numbers. The division algorithm for polynomials states that if you divide a polynomial p of x by a polynomial d of x, you get a quotient q of x and a remainder r of x. This can be written as p of x equals q of x times d of x plus r of x. The key rule is that the degree of the remainder r of x must be less than the degree of the divisor d of x. Let's start with division by a linear polynomial. Find the quotient and remainder when x cubed minus x squared minus 3, x minus 5 is divided by x minus 3. We set up the long division. First we ask, what do we multiply x by to get x cubed? The answer is x squared. We write x squared in the quotient. Then we multiply x squared by the divisor and x minus 3 to get x cubed minus 3x squared. We subtract this from the dividend. X cubed minus x cubed is 0. Negative x squared minus negative 3x squared is 2x squared. We bring down the next term, negative 3x. Now we repeat the process. What do we multiply x by to get 2x squared? The answer is 2x. We write 2x in the quotient. We multiply 2x by prox minus 3 to get 2x squared minus 6x. We subtract this. 2x squared minus 2x squared is 0. Negative 3x minus negative 6x is 3x. We bring down the last term, negative 5. One more time. What do we multiply x by to get 3x? The answer is 3. We write 3 in the quotient. We multiply 3 by x minus 3 to get 3x minus 9. We subtract this. 3x minus 3x is 0. Negative 5 minus negative 9 is 4. The remainder is 4. So, the quotient q of x is x squared plus 2x plus 3, and the remainder r is 4. We can write this as x cubed minus x squared minus 3, x minus 5 equals x squared plus 2x plus 3 times x minus 3 plus 4. It's very important to include zero coefficients for any missing terms in the dividend. Let's divide x to the 4th plus 2x squared minus 1 by x plus 3. Notice that the dividend is missing an x cubed term and an x term. We must write them in with zero coefficients. We set up the division with 0x cubed and 0x. The process is the same. We find the quotient term by term, multiply, and subtract. After several steps, we find the quotient is x cubed minus 3x squared plus 11x minus 33, and the remainder is 98. The same algorithm works for dividing by a quadratic or higher degree polynomial. The only difference is that the remainder will have a degree less than the divisor. For example, if we divide by a quadratic, the remainder will be a linear polynomial, ex plus f, or a constant if e is 0. We have now learned how to perform polynomial long division, including the important step of using zero coefficients, meeting our final objective. Let's quickly recap what we've covered today. We started by introducing the imaginary number, I, to solve quadratic equations with negative discriminants, leading us to complex solutions. We then learned how to perform the 4 basic arithmetic operations: addition, subtraction, multiplication, and division, with complex numbers. We saw how the equality of complex numbers allows us to solve for real variables. We also explored the properties of complex conjugates and proved the conjugate root theorem, which states that complex roots of real polynomials always come in conjugate pairs. Finally, we moved on to polynomials, defining them and mastering the algorithms for addition, subtraction, multiplication, and long division. These concepts are foundational for many areas of mathematics and science. To solidify your understanding, here are some practice questions. Take a moment to work through these problems. The answers will be provided on the next slide. Here are the solutions to the practice questions. Check your work carefully. For question 1, the discriminant is -4, leading to complex solutions. For question 2, we perform the operations step by step. For question 3, we use the conjugate root theorem to find the other root and then reconstruct the quadratic. For question 4, we expand the cubic. And for question 5, we use polynomial long division. If you got these correct, great job! If not, go back and review the relevant sections of the video. Practice is key to mastering these concepts. Thank you for watching. I hope this video has helped you build a strong foundation in complex numbers and polynomials.